The ground does not shake the way you expect. There is no single violent lurch. Instead, standing at the edge of a South Korean building dock on a gray morning, you feel it in your chest first, a low, sustained pressure, like a speaker playing a note too deep for the ear. Then you look up. Moving above you, with an almost absurd slowness, is a steel structure so wide that its two legs are separated by more than 130 meters of open air. Suspended from its crossbeam, hanging on wire rope thicker than a man's thigh, is a ship's bow section weighing somewhere in the region of 900 metric tons. The section drifts sideways at roughly 4 meters per minute and then stops, positioned with centimeter precision over the keel blocks below. The crane has not wavered. Its girder has not visibly bent. And you are left standing there wondering how any structure that wide, carrying that much weight so far from its own supports, has not simply folded in half. That is the question this episode answers. A gantry crane spanning 130 meters is not just a large crane. It is a fundamentally different engineering problem from anything most people have imagined when they picture a crane. The common mental image is a tower crane on a city building site, a slender vertical mast with a horizontal jib, balanced around a central pivot. That logic, intuitive as it feels, does not apply here at all. What you are looking at a major shipyard is closer to a self-propelled steel bridge, one that carries its own moving load, rolls on rails laid into the ground, and must resist forces that attack it from directions that change every single time the hook moves. By the end of this, you will be able to explain to someone exactly why those legs are that far apart, and why moving them even slightly closer together would cause the whole machine to try to tip over. The shipyard that makes this machine necessary is Hyundai Heavy Industries at Ulsan, South Korea, one of the largest single shipbuilding complexes on Earth, covering a dry dock area so large that ships over 300 meters long are assembled in modular sections before the hull is floated out complete. The Goliath gantry cranes operating above those docks carry rated lifting capacities ranging from roughly 600 to 900 metric tons, with spans, the horizontal distance between the two running legs, reaching approximately 130 meters or beyond. For reference, an American football field including both end zones is roughly 109 meters long. These cranes are wider than that, in their leg-to-leg dimension, and they roll along the dock on rail gauges matched to that span. Now here is the physics that drives all of it. When any crane lifts a load, that load exerts a downward force. Simple enough. But when the load is suspended not at the center of the crane but out toward one side, which is almost always the case in a shipyard, where you are picking up an irregular section and placing it precisely on a hull, the force is no longer symmetric. One leg of the crane is being pushed down harder than the other. Engineers call this an asymmetric or eccentric load, and it creates something more dangerous than simple compression. It creates an overturning moment. Think of it this way. If you hold a heavy shopping bag in one hand while standing on ice, your weight shifts. The further the bag swings out from your center, the harder the ice must push back under your opposite foot to stop you from tipping. If your feet are close together, that correction force must be enormous, and if the bag swings far enough, the ice under your far foot lifts entirely and you fall. Now imagine your feet are 130 meters apart. The bag can swing a very long way from center before the tipping moment exceeds what the far foot can resist by simply pressing down. That is the first reason these cranes are so wide. The leg gauge is not primarily about fitting the ship underneath, it is about keeping the machine's effective base wide enough that no asymmetric hook position can generate an overturning moment large enough to lift the windward rail. Engineers work with a quantity called the stability ratio, the relationship between the restoring moment created by the crane's own weight acting over its base and the destabilizing moment created by the offset load. Classification societies and crane standards generally require that the restoring moment exceed the overturning moment by a defined safety factor even under the most eccentric load condition the crane is rated for. Making the gauge wider directly increases the restoring moment without adding any load to the structure, which is why it is one of the most cost-effective stability tools available. But here the engineering hides a second, less obvious problem. A wider gauge means a longer girder. A longer girder, everything else being equal, deflects more under the same load. If the crossbeam of a 130-meter gantry behaved like a simple I-beam steel joist, the center of the span would sag downward by an amount that would make precision placement of a 900-ton ship section impossible. Engineers estimate that an unsupported beam of that span under that load could deflect by several hundred millimeters, in some configurations approaching a full meter at mid-span. At the tolerances required to marry two hull sections together, that is catastrophic. Which of these machines would you least want to be standing directly beneath? Tell us in the comments below. The solution is the trussed box girder, and this is where the engineering becomes genuinely elegant. Instead of a solid or even an I-section beam, the main crossbeam of a Goliath crane is built as a hollow rectangular box, typically 2 to 4 meters tall and several meters wide, whose walls are not flat steel plate but a framework of triangulated steel members, diagonals and verticals, welded into a continuous truss. Triangulation is the key mechanism. A triangle, unlike a rectangle, cannot change shape without changing the length of one of its sides. Since steel members resist length change extremely well, a triangulated structure resists deformation in a way that a simple plate or rectangular frame does not. The box format adds torsional stiffness, resistance to twisting, which matters because an asymmetric load does not just try to tip the crane, it also tries to twist the girder about its own long axis. The specific geometry of the truss members in a Goliath crane girder is engineered to place the maximum material where the bending stress is highest, at the top and bottom chords of the box, which are in compression and tension respectively when the girder is loaded from below. The web diagonals carry the shear forces between those chords. The result is a structure that, despite its enormous span, deflects by only a small fraction of what a solid beam of comparable weight would allow. The Hyundai Goliath cranes operating at Ulsan are reported to hold mid-span deflections to within a few centimeters under full load, precise enough that the trolley travel path remains functionally level. Here is the false belief that needs correcting, because it is almost universal. Most people, if they think about it at all, assume that a bigger crane is mostly a matter of using thicker steel, that you simply scale up the material and the machine scales with it. That is wrong, and it is wrong in a way that matters. Structural engineers know that as a beam span doubles, its self-weight for the same stiffness grows by roughly the cube of the span ratio, not linearly. A beam twice as long, engineered to the same deflection standard, needs roughly 8 times the material. This is why beyond certain spans, solid section beams become self-defeating. The Goliath crane's trussed box girder exists specifically to escape this scaling trap. It achieves the necessary stiffness at a fraction of the weight that a solid section would require, and this matters enormously because every kilogram of dead weight in the girder is a kilogram the legs and the rail system must carry permanently, regardless of whether the crane is lifting anything. The rail system itself is worth pausing on. Each leg of a Goliath crane sits on a bogie, a wheeled truck assembly, that runs along a rail embedded in the reinforced concrete of the dock. The rails are not standard railway track. They are heavy crane rail sections, often with a head width of 100 mm or more, and they are fastened to the dock structure with precisely calculated anchor systems designed to resist not just vertical load but the lateral forces generated when an eccentric load tries to spread the legs apart or the wind tries to push the whole crane sideways. The rail gauge must be held to within tight tolerances along the entire length of the dock, because a deviation of even a few centimeters can introduce additional bending into the legs that the structure was not designed to absorb. What you are looking at, standing at the edge of that Ulsan dock, is not a large version of a familiar thing. It is a purpose-built answer to a specific set of physics problems that only arise at this scale: the instability of asymmetric loads, the deflection penalty of long spans, the scaling trap of solid section beams, the lateral forces in the rail. Each feature of the machine is a visible response to one of those forces. The width of the legs is a stability calculation. The height of the girder is a stiffness calculation. The triangulation inside the box is a weight versus rigidity calculation. None of it is arbitrary, and none of it is decorative. That is the actual trick you can take away from this. A gantry crane is not wide because the ship underneath is wide. It is wide because the load will never hang at the center, and the only way to keep the machine from tipping is to make the distance between the rails large enough that no credible hook position can generate more overturning moment than the crane's own weight can resist. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next